Welcome to this lecture. In the last lecture we saw the different criteria for thermodynamic equilibrium across various phases. That is what is given here. This is what we saw in the last class. This is the fundamental requirement for thermodynamic equilibrium. If alpha, beta, gamma are the various phases in equilibrium, the temperature across the phases or in each of the phases must be equal. In other words, T alpha equals T beta equals T gamma and so on. This is equation 5.1. The second condition was that the pressures in the various phases must be equal to each other. P alpha equals P beta equals P gamma and so on, and the chemical potential of each of the species present in the various phases must be equal to each other. For example, if mu 1 is the chemical potential of the species 1, mu 1 in alpha must equal mu 1 in beta, must equal mu 1 in gamma and so on across all the other phases that are present. Mu 2, which is the chemical potential of species 2 in the alpha phase, must equal mu 2 in the beta phase, must equal mu 2 in the gamma phase and so on. And we can write one such equation for each of the species that are present or each of the components that are present. So, if you look at this, if there are C components that are present, we will have C such equations. Not just that, we also saw that each one of these equations is actually a composite of pi, if pi is the total number of phases, pi minus 1 equations. For example, T alpha equals T beta is one equation, T beta equals T gamma is another equation and so on and so forth. Therefore, if there are pi phases, there would be pi minus 1 different equations here, and that is valid for each one of these composite equations. This is what we saw in the last class, very fundamental, so it is good to go over it again. And then we also saw the phase rule for non-reacting systems. The way we went about deriving the phase rule was, if we are considering a system containing pi phases and the number of components is C, then we saw that the number of equations between variables was pi minus 1 into C plus 2, this we saw earlier, and the number of variables was pi into C plus 1. And we know from mathematics that if the number of variables equals the number of independent equations in a system or in a set, then we have a unique solution, or at least the number of variables must be greater than the number of independent equations connecting them. Only then will we have a possibility of realistic or meaningful solutions. If the number of variables is less than that, then we get it is not something that we would prefer. Therefore, this is the condition that we looked at, the number of variables pi into C plus 1 in a system that we are considering must be greater than or equal to pi minus 1 into C plus 2, which is the number of independent equations between them. And then if we, when we transposed this into getting a 0 on the right hand side, then we got C minus pi plus 2 must be greater than or equal to 0. In other words, if we have C minus pi plus 2 equals 0, we have a unique solution set, and if we have C minus pi plus 2 is greater than 0, then if we are able to supply that many number of variables, then the system is uniquely defined. That is essentially what this means, and this is what brought us to the concept of degrees of freedom. This is where it arises from. The degrees of freedom was C minus pi plus 2 that we saw earlier, and this is nothing but the number of variables that are short in equating the number of variables to the number of independent equations that are available. Therefore, if we supply these variables, the f number of variables, then the system is uniquely defined. Therefore, the application of phase rule tells us the number of independent variables that are required to completely specify the state of the system if the number of phases and components are known. Then we worked out an example and we started looking at the Clausius Clayperon equation. We said that the Clausius Clayperon equation is valid for any two different phases. We will typically use this when there is a phase change that is occurring, phase change at equilibrium. Therefore, we are looking at vapor liquid, solid liquid or solid vapor phases. These are the three phases that we will look at in this particular course. And we said that at equilibrium the chemical potential of a certain component between the two phases must be equal, and therefore, mu alpha must be equal to mu beta. This one determines the conditions of temperature and pressure that are specified at that particular point. So, mu alpha 1 equals mu beta 1 is the basic criterion, and then we went about deriving d mu alpha equals d mu beta. If we consider mu as a function of temperature and pressure, the easily measurable variables, then this total differential can be written in terms of the partial differentials that we have already seen, dou mu alpha dou t at constant p dt plus dou mu alpha by dou p at constant t dp equals dou mu beta dou t at constant p dt plus dou mu beta dou p at constant t dp. And then we took a detour, and I realized that I have not told you why we took the detour. We took the detour essentially to express the temperature pressure functionalities of the chemical potential in terms of the other variables on which we have a better handle. That is the reason, and also we are going to establish one other relationship where it becomes easy for our manipulations later on. When we took the detour, we started to consider this equation 215 dgt equals minus st dt plus vt dp plus sum over mu I dni, and then when we employed the reciprocity relationships that we picked up in module 2 over two combinations, I mean over two parts of this equation, the right hand side at a time, then we got that dou mu I dou p at constant t and ni was dou vt dou ni at constant Tp all other nj's, and by definition this was nothing but the partial molar volume, and similarly we got the temperature functionality as partial molar entropy. Therefore, these were the terms in the previous equation, if you recall. We will write that again, therefore, we will take a look at that, and then we also derived dou mu I by t dou t at constant p ni equals minus h I t hash by t squared. So, this is where we left off in the last class. For this, the earlier equations that we had derived was for a generic system with n number of moles and so on, and then we started to consider a pure substance. For a pure substance, we know that the partial molar properties are nothing but the properties per mole of the pure substance, and therefore, the equivalent equations, the temperature pressure functionalities of mu as well as the dou mu by t expression that we saw earlier turn out to be these special equations for 1 mole of a pure substance. Dou mu dou p at constant t equals v, which is the molar volume, dou mu dou t at constant p equals minus s, and dou mu by t dou t at constant p turns out to be minus h by t square. This is where we left off last time, and now what we will do is we will substitute these. Remember, this was a detour. We will go back from the detour to considering the case of equilibrium of a pure substance between two phases. This was the equation that we had gotten by equating d mu alpha equals d mu beta, that is what fell down, and this was equation 5.10, at which point we took a detour. Now we are going to substitute for these expressions in terms of 516, 517. Dou mu alpha dou t at constant p was nothing but minus S alpha that we saw for 1 mole of a pure substance, therefore minus S alpha dt, plus dou mu alpha dou p at constant t we found was V alpha, the molar volume in the alpha phase of the pure substance, dp is equals minus S beta dt plus V beta dp, and just taking dp dt and writing it as the derivative. These are differentials and we are getting the derivative from that. If we do that, dp dt equals S alpha minus S beta by V alpha minus V beta. The earlier these were differentials which can be interpreted as these small distances on a graph, a geometrical interpretation, and we know that that can be interpreted as a derivative as long as the dimensions that are considered are extremely small in the limit that tends to 0 and so on. dp dt equals S alpha minus S beta divided by V alpha minus V beta. We will call this equation 5.19 or 519. This is a nice expression, but this is not very useful. So, we will make it a little more useful, because P, T and V are fine, we also have entropies here which are not very easily measurable or as easily measurable as P, T and V are. To do that, let us consider this. At equilibrium, the transition between the two phases can be considered to be reversible. You know, the rate of one process in one direction equals the rate of the other process in the other direction and so on, and it is a good assumption to consider that process as reversible. If we consider the process as reversible, we can use the second law statement and the second law definition, and also okay, we will consider this a little later. We just by considering the second law conditions, we can write S alpha minus S beta, that is delta S in this case, equals Q reversible by T. This was the statement of the second law, then that we are applying to this particular case of phase change, Q reversible by T. And now let us bring in this fact: the heat goes only towards changing the phase, and therefore this Q reversible can be replaced by the difference in enthalpy between the two phases. There is nothing else that is happening there. The heat interaction goes directly towards changing the phase. Therefore, the Q reversible for this particular process can be replaced by the delta H, which happens to be H alpha minus H beta. Therefore, S alpha minus S beta becomes equal to H alpha minus H beta by T, which can be written as L by T, where L is the latent heat of the phase change. We will call this equation 520. Note that this is latent heat for the phase change, and it is not limited only to the liquid to vapor change, which is typically given in textbooks to begin with. This is applicable for the latent heat of vaporization, latent heat of melting or sublimation. Therefore, we can write equation 519 as dp dt, which is going to replace the S alpha minus S beta by L by T, and delta V was V alpha minus V beta, the change in specific volume between the two phases. Let us call this equation 521. This equation is called the Clausius Clayperon equation, and this is valid for phase changes as we had seen, because those were the conditions under which we derived it. We had assumed equilibrium conditions for a phase change and reversible conditions for a phase change and derived this, and this is valid for any phase change. And going by the left hand side dP dt, it can be interpreted as the change in pressure per unit change in temperature that is needed to maintain equilibrium. Slightly abstract, take a look at it for now and then it will make sense probably much later. For the vapor liquid equilibrium or vapor solid equilibrium, the difference between the vapor volume and the liquid or the solid volume is negligible. You know, the vapor volume of a unit amount or a unit mass of a certain substance is typically tens of times the liquid volume, typically about 30 to 50 to 80 times the liquid volume for a unit mass of the substance. And there is a certain ratio here which is quite large for vapor to solid also. Therefore, this delta V, if you can recall, was nothing but, in the case of vapor liquid equilibria, V vapor minus V liquid or V gas minus V liquid. We can replace the delta V by approximately the volume of the gas itself. We are essentially neglecting the volume of the liquid or the solid here, and volume of the gas can be approximated if the gas can be considered to behave ideally. You know, under conditions of normal temperature and pressure, this is a reasonably good assumption, except if you are dealing with very tricky gases. Therefore, the volume of gas, we are going to use the ideal gas law and express it as RT by P. We will call this equation 522, and if we substitute this 522 into the Clausius Clayperon equation 521, we get d ln P dt equals approximately equals L by RT squared. Let us call this equation 523. If you are not able to see this, let us just go back a little bit. Now, what we have done essentially here is replace delta V by V gas, and this was RT by P, and therefore, if we combine all the P's together, we get dP by P equals L by T V of the vapor times dt. Integrating that, dP by P, you get the log term there and the other terms make sense. Therefore, we get d ln P dt equals L by RT squared, and this is typically a very good approximation as long as the vapor pressure is not very large. If vapor pressure is large, then be careful in using this approximation. Okay, we have looked at conditions for equilibrium, the phase rule, which are very fundamental aspects, and then we looked at Clausius Clayperon equation for the phase change. Let us work out an example. This example will take time to work out. I will first read out the problem. I will give you say about 15 minutes to think about it and work out the initial aspects, and then I will give you more time with hints to work out the final solution. Let me read out the problem first. Isopropanol, by now our popular substance, is evaporating under pure substance conditions at 87.4 degrees C and 1 bar. It is evaporating under pure substance conditions, which means that the temperature and pressure correspond to points on the vaporization line in a PT diagram. Assuming equilibrium conditions, what is the change in pressure per unit change in temperature that is needed to maintain equilibrium? And the data that is given here is that the latent heat of vaporization for isopropanol is minus 44 kilojoules per mole. There is a certain background to this. I would like to share that here. I had assigned my students when I taught this course for the first time to come up with problems, because that is a good way of learning the subject itself at a much higher level, and also it will contribute to other aspects such as this. And this happens to be a modified form or adapted from a problem formulated by one of my students, Akhil Sai Valluri. Please go ahead, take 15 minutes and figure out how you would go about approaching the problem, then I will give you some hints. Go ahead please. would have had time to think through this, and hopefully the thought became focused towards recognizing that this is a substance evaporating under pure substance conditions, a substance evaporating, therefore it is changing its phase from liquid to vapor, therefore it is a case of phase change, and what is required is change in pressure per unit change in temperature that is needed to maintain equilibrium, therefore the whole process is under equilibrium conditions. So what does this bring to mind? Definitely the Clausius Clayperon equation. In fact, the left hand side of the Clausius Clayperon equation dP dt is this is of course the right hand side, L by T delta V. dP dt is what is required to be calculated as a part of this particular problem. If we can find dP dt by evaluating the right hand side, in other words if we know L T delta V, we can substitute the values here and find dP dt, and that is what we need. L is already given, that is the latent heat of vaporization. So if we find T delta V, or T is also given, it is known from the problem statement, it is the temperature at which the vaporization is taking place. Therefore if we find delta V, then we are actually done. So how do you go about finding delta V is the hint that I am going to leave you with for another 15 minutes or so, let us say about 10 minutes, and let us see how you come about with the solution. Go ahead please. Okay, hopefully you would have figured out how to find out delta V. Since we are almost out of time, I am just going to give you some hints, give you time to work it out and show you the complete solution when we meet the next time. Delta V is nothing but V of the vapor minus V of the liquid, or V of gas minus V of the liquid. Therefore, you need to find a way to figure out what the molar volume of the gas phase is and molar volume of the liquid phase is. What does this bring to mind? Does this bring to mind something to do with equations of state? That is exactly what we are looking at. So, go back to what equations of state are, and this is isopropanol here. See whether you are able to find out the molar volume of the vapor and the molar volume of the liquid under the saturated conditions of the liquid vapor transition. Please take this as homework. When we meet the next time, when we begin the class, I will give you the solution. Go ahead please.